Welcome to this learning module on exfiltration, presented by Marty Wanyalista as part of the BMPFast series. Exfiltration refers to the movement of water into the ground from underground storage, and it is considered a retention system. In this module, you will learn how exfiltration works, explore two of its most common applications involving perforated pipe and underground vaults, and understand how to calculate removal effectiveness. In this lesson, we'll be covering several important topics related to exfiltration as a best management practice. We'll start by defining what exfiltration actually is and how it differs from the more commonly understood concept of infiltration. The prefix ex is key here. While infiltration refers to water moving from the open air down into the ground, exfiltration specifically describes water moving into the ground from an underground storage system. This distinction matters when we're designing and evaluating stormwater management solutions. Exfiltration is a particularly popular BMP in areas where surface space is limited, since the storage occurs below ground, either in the form of a vault or a trench with perforated pipe. This makes it a versatile option in urban and developed settings where land is at a premium. We'll also walk through how to use the worksheets within the BMPFast software to calculate the annual removal effectiveness of an exfiltration system. Protecting groundwater quality is a central concern with this type of BMP, so we'll look at what design considerations help ensure that pollutants are managed appropriately before water enters the subsurface environment. Finally, we'll tie everything together with an example project that demonstrates how to enter the relevant input information and interpret the results, including annual effectiveness and annual pollutant removal for specific design configurations. Underground stormwater management systems like vaults and exfiltration trenches are important tools when surface space is limited, which is often the case in dense urban environments. An exfiltration trench is a subsurface system that serves two functions. It stores runoff and it transports it. A common design uses perforated pipe surrounded by natural rock or pollution control media. As runoff moves through the trench, it has the opportunity to exfiltrate into the surrounding soil and eventually recharge the groundwater, provided the soil conditions and water table are favorable. The perforated pipe plays an important role here by increasing the available storage volume within the trench and encouraging exfiltration to occur along the full length of the system. A stormwater vault, on the other hand, is an underground structure designed primarily for storage. Unlike a trench, a vault does not provide transport. It simply holds the runoff in place. Vaults are commonly used in urban settings where underground storage is the most practical solution. Both trenches and vaults can be designed as either detention or retention systems. When used for detention, they help control peak discharge rates by attenuating the hydrograph, essentially slowing the release of water. When used for retention, they allow the stored water to exfiltrate into the ground below. In either case, pollution control media can be incorporated into the design to help remove contaminants from the runoff before it reaches the groundwater or downstream waterways. These types of best management practices are typically selected when there simply is not enough surface area available to accommodate conventional stormwater management approaches. When evaluating the annual effectiveness of exfiltration pipes and vaults, we treat them as retention systems, meaning the key question is how quickly the stored volume is recovered and made available for the next storm event. The foundation for this analysis comes from work published by Wanyalista in 1978 and updated by Harper in 2007. Their research quantifies annual capture effectiveness as a function of storage volume, expressed as a percentage of total annual rainfall captured on the vertical axis, plotted against the design treatment depth on the horizontal axis. For standard conditions where recovery takes up to 72 hours, you apply the removal efficiency tables, published in the Applicant's Handbook Volume 1, Appendix O, from the 2024 rule. There are 80 of those tables, organized by rainfall zone, curve number, and directly connected impervious area. The example shown here is for rainfall zone 2 with a 1-inch treatment depth. Keep in mind that interpolation between tables can be challenging when your curve number or directly connected impervious area does not fall on an exact increment of 5. Now, for systems that recover much faster, specifically in 3 hours or less, such as exfiltration trenches in limestone areas or systems using select permeable media. An upward adjustment in effectiveness is appropriate. The graph shown here allows you to make that correction. The top curve represents a 3-hour recovery time, which also corresponds to the minimum interval used in Florida to define independent storm events. At that recovery rate, the full design volume is available before the next runoff event arrives. The important practical takeaway is that the benefit of fast recovery, while real, is relatively modest for systems with large holding volumes or design treatment depths greater than about 2 inches. The adjustment is most meaningful for smaller storage volumes. This fast recovery correction has also been incorporated into the BMPFast model for those doing computational analysis. There are 2 typical cross-sectional designs commonly used for infiltration trenches. The first is designed for low exfiltration conditions, where the goal is to remove the designed water volume within 72 hours. The second is for high exfiltration conditions, where the soil permeability is sufficient to remove the designed runoff volume within just 3 hours. These 2 configurations reflect the range of soil drainage capacities that engineers must account for when designing trench systems. Exfiltration pipe is a best management practice used for on-site stormwater retention. The images here show real-world examples of this approach. One installed in an urban area about 30 years ago that is still functioning today, and another application in a residential setting. The schematic gives you a sense of how the system is designed and how it works in practice. Exfiltration vaults are another category of on-site best management practices worth examining. These structures are installed underground and are designed to store stormwater and allow it to slowly infiltrate into the surrounding soil. Unlike some other systems, exfiltration vaults do not rely on perforated pipes. They come in many different types and configurations, ranging from larger systems built to handle and release significant volumes of runoff to smaller units suited for more modest drainage areas. What they all share in common is a defined storage volume, which holds water temporarily before it exfiltrates into the ground below and around the vault. This project comes from an actual permit application and is designed to demonstrate how to use BMPFast to determine annual pollutant removal effectiveness. The scenario involves a medical plaza that is classified as high-intensity commercial due to the frequent traffic it generates. The site is currently a 2-acre general agricultural area located in the Fort Lauderdale region, and the plan is to develop it for this new use. Because the owner wants to maximize the usable land area, the preferred stormwater management approach is exfiltration vaults or pipes, which are underground systems that allow water to percolate into the surrounding soil. The building downspouts are connected directly to the pavement, and that runoff then flows into the exfiltration system. A few key design parameters are provided. The curve number for the non-directly connected impervious area, or non-DCIA, is 80. The DCIA, meaning the directly connected impervious area, is 1 acre. These values are important inputs for the analysis. In terms of water quality requirements, the performance standard must meet the impaired condition criteria because this site drains to an outstanding Florida water, or OFW, which carries a higher level of protection. One important site condition to be aware of is that there is an underground limestone rock layer that is highly permeable. A percolation value from a geotechnical report is needed to justify the design. If that percolation rate supports it, the exfiltration system can be credited accordingly. Otherwise, the design treatment volume defaults to a 3-hour drawdown standard. With that context established, we will go directly into BMPFast to enter the project data and conduct the full analysis. To get started, we enter the site and catchment information for the medical facility post-development site. The performance standard here is set for discharges to an outstanding Florida water and an impaired water body, which means we're working with the most stringent removal requirement available, 95%. The annual rainfall for this location is 64 inches, and the site falls within Zone 5. When entering the watershed characteristics, both the land use types and the event mean concentrations, or EMCs, are already built into the BMPFast software. so you don't need to look those up separately. Once all the catchment data are entered, you'll notice the performance percentage specified reflects that highest threshold of 95%, which drives the selection and sizing of the best management practices for this particular site. Using standard vault dimensions of 100 feet long, 80 feet wide, and 4 feet deep, with a void space of 96%, the system achieves an annual capture rate of 95.7%. This performance level meets both the specified standard and the net improvement standard, making it a fully compliant design solution. The surrounding rock in this area is capable of exfiltrating the stored runoff water in less than 3 hours, which supports the strong capture performance. Because the storage volume in this configuration exceeds 4 inches, a high rate of pollutant removal is expected, which aligns with the results we're seeing. To generate a summary printout of the system performance, simply enter the configuration data into the tool, and it will produce the output based on these standard manufacturer vault sizes. One option being considered involves using 1,220 feet of perforated 48-inch diameter pipe placed within a trench that is 8 feet wide and 5 feet deep. Rather than a single long run, the system would be arranged as 4 parallel trenches, each 2,980 feet in length, connected by 100-foot sections of pipe running perpendicular to those long trenches. This configuration creates an interconnected network that distributes flow across the entire system. Like the other designs being evaluated, this option achieves an annual pollutant removal rate of 95%. In some regions, groundwater protection goes beyond simple runoff management. Certain spring and estuary areas require careful attention to both the volume of water recharging the groundwater and the quality of that water in terms of nutrient concentrations. While this particular project does not require that level of analysis, it is important to understand when and why it becomes necessary. When groundwater recharge analysis is needed, absorption media is selected as the medium through which stored runoff gradually exfiltrates into the ground. This process is intentionally slow, typically occurring at a rate of only about 5 inches per hour. Because of that slow rate, it generally takes more than 3 hours to fully discharge the designed runoff volume. The benefit of this approach is that the absorption media helps filter and treat the water as it moves through, allowing for a calculated estimate of the average nutrient concentration entering the groundwater. In the BMPFast program, you can initiate this type of analysis by selecting the Yes option when prompted about groundwater discharge. For this project, we are using a vault and choosing to conduct a groundwater discharge analysis, which the program then uses to evaluate how the system performs in terms of both volume and water quality reaching the groundwater table. Now we need to add absorption media to the vault, specifically the BNG24 media. Within BMPFast, navigate to the vault you've configured for exfiltration and add the media there. Once that's done, return to the exfiltration worksheet and hit Calculate. If you haven't already done so, head over to the configuration page and make sure exfiltration is selected as your BMP type. From there, continue on to the summary page to review your results. With the media in place, the annual recharge comes out to 1.602 million gallons per year, and the average total nitrogen concentration is 0.6 milligrams per liter. To put that in perspective, without the media, the average concentration would simply equal the event mean concentration, which is 2.4 milligrams per liter. That means the BNG24 media is achieving roughly 75% removal for total nitrogen. A substantial improvement. You can also pull total phosphorus removal figures from the summary page in the same way. Another important consideration for this design is the service life of the media inside the exfiltration vault. The owner has a specific requirement here. He does not want to have to dig up the vault just to replace the media, so he needs a service life of more than 30 years. To evaluate this, we use the Tools menu and select the Exfiltration option to calculate the media service life. The vault has a bottom area of 8,000 square feet, and we are using a 2-foot depth of media, which gives us a total media volume of 16,000 cubic feet. Running that calculation through the tools, the result comes back at 50 years of service life. That well exceeds the owner's requirement of 30 years. So this design successfully meets that criterion without any need for future excavation to replace the media. To wrap up, let's review what we covered in this presentation. Exfiltration refers to the movement of water from underground storage into the surrounding ground. We looked at how trenches with perforated pipe can both store and transport runoff, while vaults are primarily used for storage. These are the fundamental components that make up an exfiltration best management practice. We also worked through how to use the worksheets in BMPFast to calculate average annual pollutant removal. The software allows you to evaluate how well an exfiltration system performs, and we demonstrated that a well-designed exfiltration system can meet even the most stringent performance standard of 95% removal. We also touched on how sorption media can be incorporated into the design to specifically target nitrogen removal. Groundwater protection is a critical consideration with any exfiltration system, so understanding how to properly design and site these systems is essential to ensuring water quality is maintained below ground. The example project brought all of these concepts together, walking through a real annual removal analysis using an exfiltration approach so you could see how the calculations and design decisions work in practice. Finally, remember to save your work. Your project file will be saved with the .bmpt file extension, so be sure to keep that file accessible for future reference or revisions. Thank you for watching, and we hope this course has given you a solid foundation for designing and evaluating exfiltration best management practices. That brings us to the end of this module on exfiltration, presented by Marty Wanjalista as part of the BMPFast series. You are encouraged to explore other learning modules to strengthen your understanding, and when you feel ready, you can apply to take the competency test. For details on that process, be sure to check out the module called Self-Test. Thank you for watching.